Hello again. I'm going to call this video Chapter 15 Video 1 because this material comes from the reading in Chapter 15 from your GOB textbook. So remember in the first video I kind of had the slide where it had the recommended reading. Also, I don't know if I emphasized, skip section 11 of Chapter 14. I think that talks about sulfur-containing compounds. I'm not going to cover that or discuss that with you right now, so you can skip that. And again, Chapter 15, the first 9 sections, and then sections 11 through 13. I am not going to cover every little detail in those sections, but you can go there and get some more information about the material I'm reviewing in these videos with you. So the last video ended with me giving you an example of how to name a ketone. It was this one that you see on the overhead, 5-bromo-4-ethyl-2-heptanone. I apologize for miscounting the atoms there. I think it was a little sloppy in the way I drew that, so I drew it more neatly just to show you how to properly count the atoms and how to go from a Lewis structure into a line drawing. So again, make sure you can do that. It's good practice for you. You should also be comfortable with going from a Lewis structure, which is, you know, the most detailed way to draw an organic molecule, but it also takes the most time. You should also be comfortable with drawing the condensed structure. So how would we do that? Let me go through, and I'll write that right beneath the line drawing. So this would be, let's see, I want you to see that as well. I guess I can do that right here and still be in the view of the camera. We could write this molecule as, you might see it like this, CH3, and then it'd have the CH2, and then it'd have, let's see, how would we draw that? Well, believe it or not, you can draw that like this, CHBr. So in a condensed structure, the elements that follow a carbon are presumed to be attached to that preceding carbon. And then what you can draw, it can get kind of confusing here, but then you could draw CH for the next carbon. And we'd probably almost have to put it in brackets, but sometimes you have to use a combination of a condensed structure and a Lewis structure or a partially expanded structure and draw the ethyl group out here, kind of pointed down. It doesn't matter if it points up or down, as I've said. And then the next carbon is a CH2. And then we have this carbonyl group. How do we draw that in a line, condensed structure? You can either draw it out, C double bond O, or you can do this, as I mentioned earlier. You can put the oxygen in parentheses. You have to do it like that to distinguish that this is a carbonyl carbon, doubly bonded oxygen, versus an ether, which is a singly bonded oxygen, and then CH3. So there would be your condensed structure of this molecule, 5-bromo-4-ethyl-2-heptanone. Here's the line drawing. Here's all the hydrogens drawn in. Let's just make sure I did that correctly. CH3, CH2, CHBr, CH with the ethyl group, CH2, C oxygen in parentheses for the carbonyl, the ketone function group, and the last methyl group on the right. So 1, 2, 3, 4 ethyl, 5-bromo. Right. So here you go. Here's all the different ways you can draw molecules. And again, I've had up on the slide, just kind of reviewing here with you. Here's the reason why I like molecular models is because you can distinguish and see the geometry differences. Here's ethanol. You can clearly see the 109.5 degree angles between any hydrogen, carbon, and oxygen, or any C-CH bond. They're all 109.5 degrees because carbon is they're all single bonds. It's a tetrahedral shape around every point. It's even, it's bent around this oxygen. There's 2 lone pairs you don't see here because molecular models don't have the ability to show lone pairs of electrons, but understand that they're there. But it's bent around the oxygen there. But that bond angle there is approximately 109.5. It's probably about 105 degrees because the lone pairs take up more space. And then if you have a aldehyde again, here is the flat nature of that. So this is 120-degree bond angle, 120 degrees. However, around this carbon, you have a tetrahedral carbon, so these are all 109.5-degree bond angles. And then if you take a ketone, same sort of thing. It's flat around this. It's 120 degrees around here. That's why it's flat in the same plane. Just like 120 degrees means it's trigonoplanar. It's all in the same plane. What I mean by the same plane is I mean along this axis here. And a ketone, again, 120-degree bond angles here around that carbon, but 109.5 degrees around those. So again, just going from an alcohol to an aldehyde, this is an oxidation. Why is that an oxidation? Because I'm removing 2 hydrogens from this structure to get me this structure. Take one of these hydrogens away and this hydrogen away, you get this molecule here. So carbon, this carbon here, the carbonyl carbon, is in a higher oxidation state than this carbon here. This is a more highly reduced form of carbon. Because these are, going from here to here or here to here, are oxidation reduction reactions. So again, now let's go into the next class of compounds, which are probably the most versatile type of organic compound in a sense, because they can form many different derivatives. From a carboxylic acid, you can make an ester. You can make an amide, and it's very versatile. And the way we name these things is not all that different from how we've named the previous functional groups. So let's just review the basics of what a carboxylic acid is. A carboxylic acid has a carbonyl group in it, but now instead of a carbon on either side, it's kind of like an aldehyde. The carboxylic acid functional group has to be at the end of a carbon chain because you have to have this particular group of atoms together. You can only have a C double bond O OH, which is called a carboxyl group. It's spelled C-A-R-B-O-X-Y-L. That's a carboxyl group. We can denote it with that way, or we can draw it like this, or in a condensed way, you might see me draw it like this, C-O-O-H, which is not so easy to understand when you first learn this stuff, so I would probably recommend that you draw it out like this to emphasize that one of the oxygens is doubly bonded to a carbon and the other one is singly bonded to a carbon. It's almost like you took a ketone and an alcohol and combined them together to create this carboxyl group. So carboxylic acids, you're familiar with them. Acetic acid, which is in vinegar, is a carboxylic acid. It only contains 2 carbon atoms. So you've seen me draw this many times in this class, but here it is, CH3C double bond OH. That's a common name. I'll give you the IUPAC name in a little bit here. But another common carboxylic acid is lactic acid, which is produced during exercise. Biochemistry is like taking organic chemistry and combining it with biology. It's extremely difficult to learn and to understand. Lactic acid is part of these metabolic pathways that are involved when we break down food or metabolize certain carbohydrates and fats and things like that. But anyway, it's a carboxylic acid, and it has an OH in it as well, so it's got 2 different functional groups in it. But it's named as a carboxylic acid because the priority here is the more highly oxidized carbon gets priority in what the compound is going to be called. And butyric acid is another common carboxylic acid that has 4 carbons. That's why it's called butyric. It's based on the hydrocarbon butane. And it stinks really bad. I mean, butyric acid comes from rancid butter. The name butyric comes from Greek or Latin for meaning butter. But carboxylic acids like this have a very pungent smell. Vinegar is we eat this stuff, but it has that acidic taste. But butyric acid is on a different level. It's much more of a pungent smell. But that's a characteristic of carboxylic acids. Whereas aldehydes smell good, carboxylic acids have the opposite effect. But what's going on here in the intermolecular forces in a carboxylic acid? They're unique because they have an OH, which has the ability to hydrogen bond to other molecules of itself, but it also can hydrogen bond to water, and it has the polar carbonyl group. Carbon's partially positive, oxygen's partially negative. So it's a very polar functional group, and therefore small carboxylic acids up to about 5 carbons tend to be water soluble. Now, why don't they dissolve after you get to like 6 or 7 carbons long? It's because when you get longer chains of carbon, as I've said with other functional groups, as the carbon chain gets longer, the molecule has a nonpolar part, the carbon chain, and it has a polar part, in this case this part. And eventually the long carbon chain wins out in determining the overall polarity of the molecule. But smaller carboxylic acids are water soluble. They're all pretty high boiling liquids because they have that strong polar functional group, and they can attract each other through dipole-dipole attractions and through hydrogen bonding. A characteristic of carboxylic acid is that they're weak acids, and we talked a little bit about this in the chapter on acids and bases. An acid, like a carboxylic acid, can donate a hydrogen just like HCl can, but it's a weak acid, so we write it as an equilibrium. It doesn't completely lose all its protons, in that not 100% of these molecules ionize. Maybe 5% or less of them actually break apart into the conjugate base. In this case, this is acetic acid ionizing into its conjugate base, acetate ion, and releasing a proton, which can also, as you know, be called a hydronium ion. But this is the shorthand way of writing a dissociation of a weak acid. But the Ka is much less than 1. But they're acidic enough that they can affect the pH of a solution and bring it down to about a pH of 2 to 4. They do have some interesting chemical reactions. They do have some, they're very useful molecules. We can make esters from them, like I said, which are used in food additives and perfumes and things like that. Another useful reaction we can use with carboxylic acids, just like we can in any inorganic acid, is acid-base reaction to make the sodium or potassium salt of a carboxylic acid. That is used for when we want to maybe convert a carboxylic acid to a solid compound or a crystalline compound to use in, for instance, in drugs or food preservatives. We might want to convert them into a solid form instead of a liquid form. This is a solid because it's an ionic compound. It has a very, very high melting point. Triglycerides, which are derivatives of carboxylic acids, will react with bases and form a derivative of a carboxylic acid called a sodium salt of a fatty acid, which is soap. So believe it or not, soap is really mostly a nonpolar molecule, but it has a polar end to it. And this is why they are effective at cleaning things, because soaps have the ability to dissolve in water because they have a polar end to them, and they're electrically charged, so they interact with water very well. But they also have this long chain, which is, as I said, a nonpolar part. This is the part that will interact with the dirt or the grease and oil, so I guess, and will dissolve the oil, and this part will dissolve in the water. So soap really bridges the gap between things that are not soluble in water and making them soluble in water. It's kind of like a, I don't want to get too far into it, but it forms a sort of a spherical cage around the dirt molecule and carries them away. It's called a miso. All right, so let's get into naming because like I've said, my main goal for all these different functional groups is for you to recognize them, know a little bit about their structure and properties, and also how to name them. And then if we have time in another video, I might go through a few more of the chemical reactions. But I want to just first get through everything with how to name them and all the different options for naming them. So let's just go through a few simple examples here. Here we have acetic acid again. That's the common name. Acetate, A-C-E-T-A-T-E, is means 2 carbons. But the IUPAC name, as you've probably presumed by now, comes from the 2-carbon hydrocarbon ethane. So to name a carboxylic acid, you drop the E and you change it to an OIC, oic, and then a space acid. So you have to add the word acid on this. There's no one suffix ending for a carboxylic acid. It has to have the word acid in it. So that's why, for instance, if you take butane, or the carboxylic acid that has 4 carbons, notice again the nice thing about simple straight chain carboxylic acids is no number is needed in the name, because just like aldehydes, the functional group of interest that is going to determine the name of the compound is always at the end of the chain, so it's always at the 1 position. So butane, there's 4 carbons here, 1, 2, 3, 4. Here's your carboxyl group at the end, so this is based on butyric, that's the common name, butyric acid, but the more formal modern name is from butane. You drop the E and add the OIC acid, butanoic acid. Again, this stuff smells pretty bad. Benzoic acid is aromatic acid, and where does that name come from? Well, again, obviously benzene, and it's got an extra carbon on it. So that's really, when you have an extra carbon on a benzene ring, it's called the benzyl, B-E-N-Z-Y-L group. So this becomes benzoic acid. Very useful compound. 2 of the most important uses of it in the past have been as a food preservative. However, this stuff is not stable for very long, so what we figured out is if you react it, since it is acidic, and you react it with base, like sodium hydroxide, you can convert it into the sodium salt, and because this is an acid, this is a base, it's a typical acid-base reaction, you get the sodium salt of this, and you get water, and this is called sodium benzoate. Notice how we name it, just kind of like an ionic compound. You name the metal first, and then you name the, so to speak, the polyatomic, but you change the ending of the acid from OIC to OATE, sodium benzoate. This is a food preservative. Look on a label of many foods, any prepackaged food or, Doritos, things like that, junk food, tends to have sodium benzoate used as a preservative. The reason why it is because when we consume it in the body, it's converted back into this, and this has been found to be antibacterial and it kills bacteria. It's very effective. But this is a much more stable form of it, so that's why they use it for shelf life. The other common use, or a derivative of benzoic acid that has been very useful in the past, is converting it into this form here. So it's pretty easy to put functional groups or different things around the ring through chemical reactions. And if you put an NH2 group on the opposite side of the C double bond OH group, you get a compound that's called 4-amino-benzoic acid. This group here, when it's on a ring, is called amino, because the nitrogen-containing compounds are called amines, A-M-I-N-E. That's a class of compounds we'll discuss last in these videos. But nevertheless, it's at the 4 position because this is the 1, 2, 3, 4. And another way to name that, as we saw in the last chapters on aromatics, is this is the para position. So another way to name this would be para, because remember I talked about ortho, meta, and para positions on an aromatic ring. When, just to quick review, in case you're wondering where I'm getting this from, the ortho position to this group would be right next to it, so it'd be either here or here. The meta position to this group would be 2 carbons away, so either here or here. The para position, there's only one, it's opposite side of the ring. So another name for this compound is para-amino benzoic acid. And if you take the P of this, the A, the B, and the A, you get an acronym, PABA, P-A-B-A, and they used to capitalize it like this. This was used in sunscreens. It might still be used in sunscreens. They found that it can be sort of not toxic, but can cause allergies and skin allergies in people, so I think they've tried to limit its use in sunscreen. But molecules like this with benzene and this group here can absorb ultraviolet light, so that's how they use them in sunscreens. They absorb the light and convert it into heat instead of your skin cells absorbing the ultraviolet rays. It acts as a shield. So let's continue here with naming some of these. Let's get a little bit more sophisticated. So take, for example, this compound here. I noticed there's in the GOB text in chapter 15, there's a minor error in one of the examples, and this is the example. I think they just flipped the names. I've noticed quite a few, not a lot, but some mistakes in that textbook. So if you read something and it doesn't sound right, it might be a mistake. So just trust your instincts, and if you have a question about it, send me an email, because I don't want you to read the wrong information. So in this example, they give you a compound like this, and it has a chlorine atom in it. So again, you should recognize that this is going to be named as a carboxylic acid, because here's your main functional group. That's going to get position number 1. So here I've drawn the line drawing of it as well. 1, 2, 3, 4 carbons long. There's my 4 carbons here in the line drawing. The chlorine's attached at the end at the 4 position. So just like we've named the rest of these molecules, it's you name the substituents first, 4-chloro, and that takes care of everything. So just name it butanoic acid. Make sure there's a space in between the C and the A here. The more common name would be 4-chlorobutyric acid. Either one of those are acceptable names for a compound like that. This example here, take a look at this. Let's see, we got 1, 2, 3, 4 carbons in the longest chain, a bromine at this position. So very similar to this one. 2-bromo-butanoic acid or 2-bromo-butyric acid. I don't know why I just picked 4 carbons, but there's many examples that are longer chains. But if you've memorized the hydrocarbon names, you should have little issue with applying these rules to naming anything that has a longer series of carbons containing the carboxyl functional group. This one here is looks somewhat complicated, but if you just again focus on the longest chain that contains the carboxyl group, let's circle it here. It could be here, or it could be there, or it could be there. Does it really matter? I don't think so, because let's just circle that as my longest chain. This is 1, 2, 3, 4, 5. So these are at the 4 position. If I circled this as my longest chain, I'd have 1, 2, 3, 4, 5, and these would still be at the 4 position. So it shouldn't matter that I circle this one versus this one or that one. I'm sure you've seen that before. So again, naming this is pretty much the same thing. You count 1 here, 2 there, 3 there. So at the 3rd position I have a methyl, and at the 4th carbon I have 2 of them, but I have to indicate with a number all 3 of them. 3, 4, 4, and then tri for 3, redundancy again, trimethyl, no space, pentanoic acid. 5 carbons long, so it comes from pentane. Drop the E, add OIC, acid. And here's your line drawing for that acid. 1, 2, 3, 4, 4, trimethyl pentanoic acid. So, I think that's pretty straightforward. Oh, by the way, I made a model of as I've done with the others. Here is a model of acetic acid. So again, you'll see it looks very much like a ketone, but it's got the trigonoplanar geometry around this carbon, of course. But it's got this OH group on the end. So here is your acidic hydrogen. That hydrogen here would be like that one here, or that one here. The reason why it's acidic is because when you lose it, you create a negative charge on this oxygen. So if this ionizes, if that becomes this is now the conjugate base, this is the acetate ion. This has a negative charge on it, but oxygen being electronegative, and the fact that it's near this oxygen, that this negative charge that's being created here can be shared among these two oxygens. That's called resonance, as you know, and that's a stable sort of arrangement. So that's why this oxygen-hydrogen bond is somewhat easily broken, because the anion that you get is somewhat stable. But they're weak acids. Similar structure to ketones and aldehydes, though. So let's go on to the next class. What can you do with carboxylic acids? How do you make them? Well, you can make them, how do you make esters? Well, you use a carboxylic acid and an alcohol. Let's just talk a little bit about, as I've done with the other functional groups, let's just talk a little bit about the physical properties and characteristics of esters. They have this structure, so let's just go back a few. Notice that on a carboxylic acid, I had this as my general structure, and now I have this. So what's the difference? The only difference is that this hydrogen of the carboxylic acid has been substituted with a carbon group. It can be a different carbon group from what's attached on this side, or it can be the same. It doesn't matter. It's a carbon. So it's a derivative of a carboxylic acid. It does not have the ability to hydrogen bond to itself now because it lost the hydrogen, the acidic hydrogen. It's still somewhat polar, so they are water soluble. At least the smaller esters under 5 carbons are somewhat water soluble. But the nice quality about esters is that they have this pleasant smell generally. Aldehydes and esters, since they, for whatever reason, these don't have that acidic hydrogen, so they have a more pleasant smell. But what do we do with these things, and how do we convert them to other useful things? Well, this is probably hard to see on here, but this is methyl salicylate. And I'll give you some examples again coming up, as I've done with the other groups, how to name these things. But the first part of the name, methyl, is coming from the alcohol portion, which is this part. This part came from methyl alcohol. This part here came from what's called salicylic acid, which is used to make aspirin. But this is essence of wintergreen. It's in lifesavers and in mint-flavored food and things like that. Very pleasant smelling and good tasting stuff. Another useful thing with esters is you can make polymers. I'm sure you've heard of polyester. A lot of the clothes we wear and fabrics that we use are made from polymers of esters. And they have this structure. And a polymer is a completely, it's a very important branch of chemistry, very hard to understand. We're not going to even, we're just going to touch on it here, what a polymer is. But a polymer is a word, poly, P-O-L-Y-M-E-R. The prefix poly means many things. And so you take a monomer, which is the building block of a polymer, and you repeat it anywhere from 100 to as many as 10,000 times. It's almost impossible to tell, even with all our technology, how long these chains are, because they are so intertwined on a microscopic level. You can't really see individual molecules, so to speak. It's hard to do. We kind of just give an average molecular weight, so that N is some range of repeating units. But polymers are almost like pieces of spaghetti in There's just very long, proteins are polymers, DNA is a polymer, biological polymer, but they're very, very important compounds. But if you take this diacid, it's called, so it's got a carboxylic acid on both ends of the molecule of benzene ring, and if you mix it with a molecule that's has two alcohol groups on the end, and you heat it under the right conditions, you can string these things together in very long chains, and they become polyester. They become materials that are very, very durable, very chemically stable. That's why we use them to make clothes. We use polyesters in PET bottles, those plastic bottles that we all drink from, disposable water, and the more permanent ones that you carry around for water bottles. Those are made out of chains of polyesters or ester linkages. This is your ester linkage, the C double bond O, single bond O to carbon on this side and carbon on that side. That is what we call an ester. Very important stuff. Dacron is a version of polyester it's a fabric. Rayon, R-A-Y-O-N, is another form of polyester. They're used in coatings, all sorts of places. Again, the polarity of a ester group is similar to a carboxylic acid. It's got this polar carbonyl. It's got the nonpolar carbon chains. So there's sort of a competition. Esters are made up of a nonpolar part and a polar part, just like carboxylic acids are. Some of the important things about esters is due to their fragrant odors, they're used in perfumes, food flavoring,